So hi everyone, hopefully you can hear me on the internet too. Thanks for coming today. So our presenter is Shubham Kanodia. Shubham completed his master's in physics at Brown University, followed by his PhD in astronomy at Penn State. Currently, he's a Carnegie postdoctoral fellow at Carnegie's Earth and Planets Lab, where his research focuses on studying the intersection between giant planets and M dwarfs by combining different observational and statistical techniques. Without further ado, please take it away.
Thank you, Colin. Thank you, everyone, for
Who do you work with at Brown?
Greg Tucker
Okay, nice.
on a balloon
Do you
borne
know
mission to study
Yeah.
exoplanet
Well,
atmospheres.
yeah.
Yeah,
you know
Peter
Peter
Hagler.
Hagler's here.
Uh-huh.
Yeah. Did you talk to him?
I had not today, but
Okay.
yes, I met him last year, I think.
Okay. Small world. Yeah.
Yeah. But I'm quite excited to be here, especially because we've been trying to organize this visit for more than a year now. And finally, of course, it's this chaotic week, but hopefully we can dive into the world of science for an hour. And so as you can gauge from the title of my talk, I'm interested in giant planets. And as Callan said, I'm interested in M dwarfs and the intersection between M dwarfs and giant planets. And I want to talk about how the projects that I'll be discussing today are helping us utilize the stellar mass axis as a means of testing and breaking our planet formation and statistical models and trying to find out how we can fix them. All right, so let's get started. Where's my cursor? There. And I should definitely mention the fact that all of the work I'll be presenting here has been made possible by these wonderful collaborators spanning a lot of different places, including Goddard, including many people in this room itself. And so it's only possible because of all of their contributions and the effort that they have put in, as well as the funding agencies, including NASA. So when I think about exoplanets, I think there's one really big science goal that drives the field forward, and that is to understand the solar system's formation. We exist on Earth in a system with 8 planets, but we still do not exactly know how did the solar system form. What is the role of each planet in the formation of the Earth, but also the habitability of the Earth? And the solar system is our ground truth, basically. But the problem is that's the only one we have. And when it comes to planet formation, what we've realized in the past few decades is that it's a fairly stochastic process. And when you have a stochastic process, you need a large sample size to marginalize over the uncertainties in your stochastic process. And that's where exoplanets come in. We can try and combine the lessons, the detailed models, the detailed interior models from the solar system, the detailed formation models that we base of the solar system, and statistics from these exoplanets to drive the field forward. And I'm going to give some examples of how we are doing that as part of the GEMS collaboration. GEMS is referring to giant exoplanets around M dwarf stars. So you'll see that acronym come forward a few times in this talk. But I mentioned the solar system, so let's start over there. And I'll be showing this plot a few times. So let me just make sure we all understand and are comfortable with this. Where on the x-axis, I have the semi-major axis. How far is the planet from the host star? On the y-axis, I have the mass of the planet. On the left, it's Earth masses. On the right, it's Jupiter masses. And for the purposes of this talk, I'm mainly interested in the gas giants. So if we zoom into those, we just have 2 giant planets in the solar system. And while with 2 planets, you can do some statistics, you can probably fit a line. You probably should not do much more than that. And up until 1995, that was the best we could do because we had just 2 known giant planets. It was very limiting when it comes to understanding planet formation, planet interiors, most things about exoplanets or planets as a whole. But soon we had 51 PEG, and in just about a year, we had more than a few planets. We had about 10 giant planets that we knew of. And the first thing I want to draw your attention to immediately, even in the first year, is the fact that these are not solar system-like. Their orbital separations are much closer in compared to the solar system. And that's important because even fast forward 30 years to the present, even when we have about 1,000 giant planets in this part of parameter space, most of them are not solar system-like. They're much closer to their host star for a whole number of detection biases and reasons, which I'm happy to get into later if people are interested. But the end result is that our current sample of giant planets does not really represent the solar system-like planets or the architectures. And therefore, it's difficult to draw a direct line between the two. What I want to show you through this talk is if we expand this into the 3rd dimension, which is stellar mass. So now the colors are the mass of the host stars, where lighter stars are green, darker stars are blue. Actually, moving on to lower host stars is how is it helping us marginalize over some of these uncertainties and actually draw those connections with the solar system planets that have been harder to do so far. And that's going to be kind of the thrust of my talk, expanding a dimensionality into other dimensions. In this case, I'll be talking about stellar mass and then eventually semi-major axis as well, as a means of connecting the extrasolar planet and solar planet populations. All right, so M-dwarfs. I know there are a few aficionados in the room, but let's just make sure we all understand some of the M-dwarf terminology and the numbers and what makes these stars so unique. And the first thing is the fact that these stars are much smaller and colder than the sun. They range from about 10% to 60% that of the sun in mass and radius. Their temperatures are much colder. Therefore, the artist animation on the right shows you how these stars are much redder than the sun. Because they are smaller and redder, their luminosities are much smaller. They're very, very faint stars from about 1,000th that of the sun to about the 10th that of the sun. And because they are so faint and low luminosity, they burn hydrogen to helium very, very slowly. So basically, they have infinite lifetimes compared to most other main sequence stars that we can think about. And that's important when it comes to planet formation, because the pre-main sequence lifetimes through which planets form and evolve are different for these stars. The main sequence lifetimes are very different for these stars. Any M-dwarf that's ever been born has never died, has never evolved off the main sequence because they evolve so slowly. And that has very important ramifications when we think about planets around these types of stars. And lastly, what these stars are infamous for, which is their flares and their spot activities, the coronal mass ejections, and so on. And again, you can see that immediately from the artist's conception on the bottom right. These stars are very heterogeneous in terms of their photospheres. They have a lot of spots, faculae, very frequent flaring, and that can have, again, very important ramifications for how planets form and evolve. And I'll be trying to discuss some of that today. But the first question I think we should answer, or try to answer, is why do we care about M-dwarf stars? Earth does not orbit an M-dwarf, and if we care about solar system-like planets, why do we care about M-dwarf stars? And I think the reason behind that is because the majority of the stars in the galaxy are orbiting M-dwarfs. As you can see from the histogram on the right, this is just the 10 parsec sample, and about 75% of the stars in our local neighborhood are M-dwarf stars. Another way to think about this is this artist's rendition of the night sky. This is how the night sky you can see from the naked eye. But now if you had a slightly larger eye and slightly more sensitive in the red, this is the version of the night sky you would see just from Earth itself. And the main reason behind that is because our sky is full of these M-dwarf stars. We just cannot see them because they're red and faint. But from a practical point of view, what's also important to consider is because these stars are so much smaller than the sun, they represent the extremes of planet formation. And therefore, they're a very nice test bed to break our theories, which we understand very poorly, and figure out how to fix them. And then again, because the stars are smaller and redder and fainter, it should be easier to detect planets around them just because their planetary amplitudes should be enhanced. So the stars are important, they're numerous, and they represent, I would hope, some practical advantages to studying planets around them. But are planets around M-dwarf stars different? Can we just take an Earth-like planet, study it around a solar-type star, and call it done and just assume all planets around all types of the stars are similar? And the answer is not really, because our theoretical expectations suggest that the way planets form in protoplanetary disks, those protoplanetary disks look very different around M-dwarf stars. Not just theory, we have empirical evidence which suggests from missions from radial velocity to transit missions such as Kepler K2, that the number of planets and the properties of planets when it comes to small planets are different for M-dwarf stars. And that's what this plot on the right is showing, where in the x-axis you have stellar temperature, stars to the left are cooler, so M-dwarfs is the leftmost bin. There are just many more small planets around M-dwarf stars. So as far as we can tell, small planets around M-dwarf stars are indeed different, both in their properties and their numbers, than their FGK counterparts. But the big question that I want you to think about is, what about the giant planets? What about the giant planets around M-dwarf stars? And that's where the GEMS work comes in. I do not refer to these GEMS. Being at Carnegie Earth and Planets Lab, where I have a lot of geologist colleagues, I have to specify and break their hearts open that these aren't the GEMS I'm interested in, but I'm interested in giant exoplanets around M-dwarf stars. And the work I'll be presenting today is broken down into these two subgroups. So we have the GEMS collaboration, which has a ground-based component, which is how we are finding these really rare planets, the Searching for GEMS survey, as well as the space-based component, which we are doing with JWST, and trying to observe the atmospheres of these planets. So let's start from the ground. where we are trying to find these planets. But the problem is we just had 2 of these planets up until a few years back. And as I said, with 2 planets, with a sample size of 2, it's really hard to do some statistics. And one might wonder, why is that? And despite the fact that these stars are small, the planetary signal should be really large, because a big planet around a small star should give you a whopping signal. But the problem is these planets are faint, but also most of our instruments were built to look at the type of the sky on the left, which is Kepler or HARPS, which are focused on solar type stars, which is what I've shown in the blue. But most of these M dwarfs are much redder than Kepler or HARPS. And if you want to go from the version of the sky on the left to the version on the right, we need instruments that can observe or are efficient at capturing light that's much redder than what the sun emits in. And that's some of the instrumentation work I did trying to build the Habitable Zone Planet Finder, which is HPF. So this is a purpose-built instrument, a radial velocity spectrograph, that's built to find planets around low mass stars, mid to late M dwarfs. And you can gauge that from its wavelength coverage, as well as NUID, which is the sister spectrograph to HPF, which is built to find planets around solar type stars, but because of its large wavelength coverage, can find planets down to the early M's. And Mike was also a part of the NUID team. I won't be discussing a lot of the instrumentation today, but I'm happy to answer any questions about the. Sorry. And I'll be happy to answer any questions. Ravi's trying not to answer any questions. But because of HPF and NUID, now we can actually observe some of these really faint and really red stars. We can go from the version of the sky on the left, which is purpose-built to find planets around solar type stars, to the version of the sky on the right. Now we can cover these really redder and near infrared wavelengths. But the next revolution when it comes to the GEMS was NASA's TESS mission. As by virtue of its all-sky coverage and the fact that it's looking at so many M dwarfs, we have been able to combine the power of TESS as well as HPF, NUID, and some of these other radial velocity spectrographs to increase the sample from 2 to closer to about 30 in about 5 odd years or so. And the detections from our survey are shown in orange, as well as the ones we are working on this year as the final bar in that bar plot. And most of these planets have been led by students, including Angeli, who's working with Nicole and Caleb right here on some of these planets and finding them, characterizing them, understanding how they form and how they fit into this population. So this is proven to be a really nice effort to train students as well, because the planets are so easy to find once we know they exist, because they just have such large amplitudes. But I'll be discussing one of my favorite planets, TOI 5205, and trying to drive this story forward based on this planet. So this was called the Forbidden Planet by some press releases. And the reason for that is really interesting. So this is a Jupiter-sized, Jupiter-mass planet, but it's orbiting a star that's only 40% that of the sun. So it's a pretty cold, pretty low mass M dwarf. So you're taking a Jupiter, you're somehow trying to form it around a star that's just about 40% the mass of the sun. It's orbiting at a period of just about 1.5 days. But because the star is so cold, the planet has a temperature of just about 700 odd Kelvin. So cold, but he's so close to the star, but still not a canonical hot Jupiter, still fairly cold by most exoplanet standards. What's interesting is that it has a really large transit depth. The planet is, because it's so big around a star that's so small, it has one of the deepest known transits of all known transiting exoplanets. But the reason it's forbidden by our classical formation models is the fact that based on ALMA observations of protoplanetary disks, we expect very little material in a median M dwarf disk. The exact number doesn't matter. It's on the order of about 10 Earth masses of material in the median M dwarf disk. If we take some planet interior models and try to predict the properties of TOI 5205, we expect the amount of material in this planet, and by material I mean metals, heavy elements, to be about 5 times, 6 times the amount of material present in the protoplanetary disks. And that's the problem. Planet formation cannot be greater than 100% efficient, so something has to give in one of those quantities. Either there's more material in the disk or there's less material in the stars, in the planet, sorry. So because I'll be discussing planet formation a little bit through this talk, let's just make sure we understand a little bit about the various stages.
Could it form like a star?
Excellent question. And I'll be discussing some of that.
What was the
Could it form like a star?
binary?
Like a binary
Like a
star,
binary
yeah.
star.
So instead of forming in a protoplanetary disk, so to Mike's question, so stars typically form in the class 0 phase where you start off with a giant molecular cloud, and if you're forming like a star, before the cloud collapses, you exceed the Rayleigh-Jeans criteria and you start to collapse and form stars. If you're much smaller, instead of forming stars, you'll start to form a disk. So that's the class 1 phase, where your actual host star is still embedded within the cloud. And you don't really have that pancake disk which you have in the class 2 phase. And the class 2 phase is typically where we think most planets form, be it giant planets or small planets, through the conventional methods of formation, which is core accretion. And core accretion is basically where you're forming this really massive core on the order of 10 to 20 Earth masses. And then once you have a core which crosses a certain threshold, it starts to initiate this runaway process of gaseous accretion, and that's how you form an object like Jupiter, we think. And that's where most of the planet's mass is in its gaseous content. The alternate is what takes place in the class 0/1 phase is gravitational instability. So this is an animation that shows a simulation of gravitational instability. So this was proposed by Alan Bass in 1997. So this is not exactly stellar-like formation, but this predates core accretion. And star formation predates gravitational instability as well. So you're talking about 3 methods of formation. I'm discussing 2 of them over here. For most of our giant planets, be it on any type of star, we do not think they should form like stars, because most stellar formation takes place when the ratio between the primary and the secondary is not that asymmetric. It's very hard to form stars where the Q, or the ratio of the star to the secondary, is too far from 1. And that's the main reason why I'm hesitant to say that it could have formed like a star. And I'm mainly going with these 2 formation mechanisms, gravitational instability and core accretion. Yes.
Why not an encounter?
Yes, so that's a very good possibility that maybe this did not form in the same disk or environment as the M dwarf. Maybe it was captured by one of the free floating planets and then it was captured by the M dwarf star. I think that's very, very possible. We just don't have very good statistics on the number of the free floating planets at the moment. There's a lot of JWST programs trying to constrain those exact numbers. I think once we have a good constraint on those numbers, what's the number density of free floating planets? We can try to do some n-body simulations to see how often can you take one of those free floating planets and capture them by a star which has a very small gravitational potential.
We do a galaxy comparison between the planet and the star and see if it's in the same history.
Yes and no. I think for that we will need elemental abundances. And for M dwarfs, that's extremely hard. There's very few M dwarfs of which we have elemental abundances, and I'll discuss some of that, why that is. But in principle, it's hard to take just the metallicity of the planet and just the metallicity of the star, because there's so many processes that take place during the class 2-3 phase that influence the metallicity of both those objects, even after they are formed. And we have very little handle on what those processes are or what their timescales are. And the time scale does matter, because when you're comparing these 2 formation processes, gravitational instability and core accretion, that's one of the biggest driving differentiators between the 2. One of the biggest drawbacks of core accretion is that it takes a really long time to take place, because you need to form this rocky core before you can initiate that runaway process. And that rocky core takes a while to form. Around an M dwarf star, it takes even longer to form. So you have the mass problem and the timescale problem for forming giant planets around M dwarf stars. So let's look at that in a slightly more detailed manner. When I was talking about 5205, I was referring to protoplanetary disks. And this is the current landscape for protoplanetary disks. The protoplanetary disks in which giant planets form, this is their dust mass as measured from ALMA with certain approximations. There's lots of caveats to this. I'm happy to discuss those later. But what I'm showing on the x-axis is the mass of the host star for these class 2 objects. On the y-axis, I have the mass of the disks in dust. And the line and the shaded region basically shows your 50th percentile and the 1 sigma around that. So the first thing I want you to notice is the huge scatter. We have a tentative trend, which has been fairly well confirmed and established by now, that the average disk mass trends with the host star mass, but there's a lot of scatter around that. So that's the first point I want you to notice. And that's important to consider, because when I plot the giant planet interior heavy element masses, now that's in the triangle, those are much higher than the median value. So it's impossible to form these giant planets in a median M dwarf disk. Maybe that's not too surprising. We know these planets are rare. It doesn't really take too much to figure out and put 2 and 2 together and say that they don't form in an average M dwarf disk. The problem is, even in these really massive M dwarf disks, let's see, where's my cursor? Like this one, you cannot just say that there's enough material in those disks to form those planets because formation is not 100% efficient. Once I take into account the typical formation efficiency, which is about a factor of 10, I need a disk which has at least 10 times the amount of material present in the planet. And that's really the problem. I need disks that are really, really massive somewhere over here. That's partially ameliorated by the fact that we can maybe start invoking formation in much earlier disks in class 0/1 stages when the disks are more massive, or the fact that maybe we are underestimating the disk masses. And there's more than ample evidence that suggests that we are probably doing this by maybe even an order of magnitude for most of the disks. There isn't an unbiased sample from ALMA to probe this in a statistical sense yet. And therefore, we had proposed an ALMA observation, a pilot program to do this for 3 disks, which unfortunately did not get accepted. But since then, there have been a lot of other studies which have suggested other ways to do that. And hopefully, there are some other programs in the future. But the main point is, can we provide an unbiased sample which measures the true dust mass of these disks in which planets form and compare that with the actual planet masses? And that's hard to do at the moment. Yes.
So how is it possible to underestimate disk mass if it's coming from observations? What does it mean?
Yeah, so we are measuring the disk dust masses for this sample, and which is how it's done for most of the disks because it's the cheapest way to do it in terms of telescope time, by measuring the 850 micron emission. So the 850 micron emission is a continuum emission of the disks. And at 850 microns, the assumption is that you're measuring the one part of the SED, and then you use some scaling laws to assume the index of the SED and derive the total mass. The problem is that by
extrapolation.
Yeah, that's, I think.
Exactly.
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 Yeah, we run the same stuff when we talk about masses of debris disks, stuff
Yeah,
like that.
right.
Size distribution is a huge issue.
Exactly. So it's the size distribution and the fact that by the time we reach the class 2 phase, most of the dust we think is locked up in much more massive particles. So if we were to make a version of this with, say, VLA data at 3 millimeters, things would look very different. And we would not get the same disk mass. But at the moment, we have many more ALMA disks than we have VLA disks because of difference in ages and lots of other factors. But the other option is I could move those green triangles lower down. Maybe I'm underestimating those giant planet metalicities. And in fact, now we are understanding that most of our giant exoplanet models are overly simplistic. If you look at Juno and Cassini and the solar system, we know that these planets are incredibly complex. They have these fuzzy cores. They have this transition zone between the core and the envelope. In fact, we don't think there's a separate core and the envelope. We think there's this region of transition where helium becomes insoluble in hydrogen because of the temperature pressure conditions. There's a phase transition, helium rains out, there's a latent heat from that phase transition that puffs up the planet. There's convective mixing, there's ammonia mush balls, there's vertical jets, there's all sorts of wonderful complexities. And the bottom line is that our solar system planets are telling us that our exoplanet models are wrong, basically. And they're just completely inaccurate, but they are the best we can do. So the question is, how can we combine measurements from Juno and Cassini for these objects that do not look like our exoplanets to test our exoplanet interior models and improve them? So that's what I'm trying to do with 5205, and I'll give you an example of that. So hopefully we can combine these two sources of reconciliation to improve our disk dust masses, to reduce our giant planet mass metallicities, and then maybe reconcile things with core accretion, which has been our workhorse, our canonical conventional model of giant planet formation. But the other option is gravitational instability, which is the top-down approach, where you have objects forming in these really massive early disks. I showed 3 of those seed particles over there, and this is work done by Alan Boss a couple of years back now, where we tried to do some population synthesis on trying to predict what kinds of initial conditions do you require to form giant planets around M-dwarf stars. So ranging from different disk masses, different stellar masses on the Y and X axis respectively, we're trying to predict what is the frequency of giant planets we can form. And I would treat this color bar in a relative sense. So the darker colors say basically you can form more giant planets, lighter colors say you can form less giant planets. And the point is, based on the VLA sample of protostellar objects, we do have disks that are so massive that they can form some of these giant planets based on our formation simulations. But there's caveats to that, because VLA is not measuring host star masses because it's measuring embedded objects, et cetera, et cetera. I'm happy to go into those later. There's lots of caveats to that. I think the takeaway over here that you should think about is that for most of the more massive stars, so by more massive stars, I mean FGK and early M's, you need disks that are on the order of 10% the host star mass. And as you go towards lower and lower mass stars, that ratio becomes much more higher. But maybe 5205 is just an outlier. Can we move beyond these outliers and can we do some statistics? Maybe we should not care about so much about one outlier and try to see if we can do some statistics and understand planet formation, as I said, because it's a fairly stochastic process. And that's where the ground-based component of the GEM survey comes in. So what we're trying to do is look at 1 million M-dwarfs as observed by NASA's TESS mission. This is a volume-limited survey of 200 parsecs, which has about 1 million M-dwarfs within 10%. And the goal is to find about 100 transiting planets on the basis of a conservative occurrence rate estimate. So this is work we are doing, Caleb and I are doing with Roman Glusman, who's a master's student at University of Amsterdam, to try and find these objects through a rigorous pipeline that's completely decoupled from the standard TESS pipeline, because we are focused on these really faint stars, which have different properties than the typical TESS small planet stars. While we are doing that, one of the biggest problems is we have lots of astrophysical false positives. So we have students working on trying to characterize those false positives, which are brown dwarfs and eclipsing binaries for the most part. Quite often, depending on the exact subsample you're looking, the false positive rate can be 10:1. So we have a lot of astrophysical false positives that are important to consider if we care about occurrence rates. And then when we have those planets, we go out and measure their masses. And the goal is to measure the masses for 40 transiting planets with radial velocities. And the reason is because once you can do that, you can start to do some statistics. You can do statistics on the bulk properties, and you can do statistics on the atmospheric properties. So let me give you some examples of that. So when it comes to the bulk properties, let's go back to the stellar mass axis. Now I'm showing this, the planet mass as a function of stellar mass. M dwarfs are to the left of that black line. And the first thing I want to draw your attention to is that blue region on the top. So there are very few super Jupiters around M dwarf stars. Maybe that's not too surprising. If I'm saying it's hard to form a Jupiter around a low mass star, it should be much harder to form a super Jupiter around a low mass star, which are many times Jupiter's mass. But if I do some statistics over here, and I won't go into the details, but we're applying some non-parametric beta function models, which is in these Python packages that we've published called Marexo. What we see is that the average mass of a giant planet, if it has a Jupiter radius, and the Jupiter radius is important to consider because now we're excluding hot Jupiters, because none of the M dwarf giant planets are hot Jupiters. Even though orbiting so close to their host star, they're not hot in the canonical sense of the classification. So if I'm looking at these warm Jupiters and comparing them as a function of stellar mass, I see a very clear trend where more massive stars have more massive warm Jupiters. But then the next question we ask is, maybe super Jupiters form in a different way to Jupiters. And what we are seeing is a transition in formation mechanism between Jupiters and super Jupiters. And why would I ask that question? There's some previous studies to suggest that. Again, I'm happy to get into that later. But if I ask that question and start to reduce the maximum planet mass I'm considering over here, let's just say I block out half the planets. And I basically did this in steps where I'm reducing planets at 10 Jupiter masses, 4, 3, 2. At 2, I see this really weird transition that takes place. And the weird transition is that from going to care about the stellar mass to suddenly becoming impervious to the host star mass. So what we are seeing is that once I exclude super Jupiters above 2 Jupiter masses, the remaining planets do not really care about the host star mass. And the way you should think about this plot is that it's basically statistically indistinguishable from a flat line. There isn't a linear or nonlinear trend over here in the planet mass as a function of the host star mass. So these warm Jupiter bulk properties are telling us that they don't really care about the host star mass. If you do not believe these statistics, that's fine. I didn't at first either. So I just plotted a simple histogram. And the simple histogram is telling me something similar. If I consider all the planets, that's what the histogram on the right shows. The blue and the red, the FGKs and the M dwarfs, are very different. But if I exclude the super Jupiters, the qualifiers, the median, the quartile, et cetera, are very similar for the two histograms. So the FGK and the M dwarf, warm Jupiter, bulk properties are very similar. And that's weird because, again, that was not predicted by our formation models. And the way we try to explain that, coming back to the disk sample, is by trying to combine the different pieces of evidence we have. So we know that the average disk gets lower and lower in mass. We know that giant planets get rarer around M dwarf stars. But we also now know that the bulk properties, when they do exist, are similar to the FGK counterparts. So what we are proposing over here is that all the giant planets, the warm Jupiters at least, are forming in disks that are similar in their mass. They're similar in their mass, and that's the main driving factor in their bulk properties. But because those really massive disks get rarer and rarer and rarer from FGK stars to M dwarfs, the planets get rarer from FGK stars to M dwarfs. But when they do form, they have similar bulk properties. So again, as I said, we are about halfway through the survey, and hopefully by the end of the survey, we can confirm this trend and increase its statistical significance, and actually confirm this really weird result that giant planets across the stellar mass axis are probably forming in similar disks. And what's weird about this is not just they're forming in similar disk masses, but the fact that the disk mass is the dominant factor. Because there are lots of other factors that go into planet formation, like the size of the disk, the gravitational potential of the star, the surface density of the disk, but it seems to be that they still seem to be impervious of the stellar mass axis. And why is that? But the next angle that I know a lot of folks in this room are interested in and involved in, for that matter, is the JWST atmospheric characterization, and hopefully in the future with Ariel as well. So we have a large GWST survey from cycle 2, studying 7 of these gems with 18 transits, with 130 odd hours of GWST observing time. And of course, my PIs are Caleb Kanyas, Jessica Levy Roberts, and includes wonderful people, including Nicole, Janina, hope I've not missed, and Dana, of course, in this room. And what we are trying to do is take 7 of these giant planets and study their mass metallicity trend. And the mass metallicity trend, coming back to the FGKs, is this plot, where on the y-axis I have the metallicity of the atmospheres. On the x-axis I have the mass of these planets. Again, the only ground truth here is the solar system, which is shown in orange with methane. And we see that the solar system giant planets follow an inverse trend. There's lesser methane in Jupiter, there's more in Saturn, there's even more in Uranus and Neptune. So they're inversely proportional to their mass. There's tentative evidence, at least for me it's tentative, that Hubble showed this for FGK hot Jupiters, which is what's shown in the light blue points. But if we believe that to be real, we would hope to see something similar with JWST in the square, dark blue squares with water. The problem is those two are different colors. Orange is not the same as blue, methane is not the same as water. We are not able to study these two populations of planets with water and methane at the same time. The FGK planets are too hot. The methane is dissociated. Solar system planets are too cold, the water condenses out. And that's where the GEM sample comes in. So these are the simulations we have for our 7 planets based on a predicted abundance precision. And what we're hoping to do is measure water and methane across a self-consistent sample of planets. And the 7 planets have been chosen to span this range of planet mass space. And see how it compares within the same planet. How does the methane compare to the water? Is it depleted again, like we see for FGKs in the solar system? Is it impervious to the planet mass? Is it completely independent and the slope is basically 0? Or do water and methane show the same abundance in these planets? And then we can say that the processes involved in the depletion and enrichment of methane and water are different for M dwarfs than for FGK stars. So that's kind of the goal. That's one of the goals. But the second goal is, again, coming back to the solar system and refining those interior models. So this is work we are doing with Simon Mueller and Ravid Hellet at Zurich, who are taking the lessons learned from Jupiter and Saturn, from Juno and Cassini, and incorporating them into these planet synth models, which take the latest equations of state evolutionary tracks, et cetera, but also all of these observables. They take the radii from TESS, the masses from the radial velocities, and then the atmospheric properties from JWST, to give us an insight into the planetary interiors. So let me come back to 5205 as a real-world example of that. So this is the real light curve of TOI 5205 that was reduced by Dana and Caleb, which was our first observation from JWST. And the first thing I want to draw your attention to is the really huge transit. So this is 6% transit. That's real data from JWST, which is exquisite in precision. But despite that, you will see that the model does not match the data. And the problem is not the data over there. The problem is that we have a star spot crossing. In fact, we have 2 star spot crossings. And those are huge, 500 ppm star spots that would basically drown out any small planet signal that if that were orbiting this M dwarf star. And because we have the precision of JWST as well as the size of this planet, we can actually map the surface of the star and model the size of those spots. And this is one of our earlier models, and the presence of those spots, the location and the temperature of those spots. And that's important to do because when we look at the transmission spectrum, so that's the transmission spectrum. So the size of the planet is a function of wavelength, and the different features basically give you a chemical inventory of the planet. At least that's how it should be on paper. In practice, this is our model, and the biggest component in the model is the star. And the reason we have this is because of those star spots, both the occulted and the unocculted star spots. So that's the transit light source effect, the TLS effect that's become so infamous now. But we are able to model that by virtue of the fact that we have such a large transit depth, by virtue of the fact we have a large scale height, as well as the fact that we can use priors from our occulted spots to those unocculted spots. And it's important to map and understand the transit light source effect, because if I put TRAPPIST on the same scale, that's what it looks like. And it's much harder to do this for TRAPPIST. Granted, TRAPPIST is a much colder star, it's an ultra cool dwarf, so your stellar models start to become even more less believable, to put it mildly. But that's a real problem. And we really care about these small planets around M dwarf stars because all the currently known habitable zone rocky planets are orbiting M dwarfs, be it from transits or the non-transiting ones. If we care about the upcoming ELTs, any of the ones we can observe and hopefully, if we haven't read Kevin Hardegree-Ullman's recent paper, hopefully have a hope of measuring and understand and trying to find biosignatures in the near future. They're orbiting these M dwarf stars. And that's why it's really important to not just observe these stars, but observe the planets and understand what's going on around these stars. And they're having some wonderful observations with JWST, which are already doing that for small planets, but they're all flat and featureless so far. And that's the problem, that despite the fact that the stars are small and we have the wonderful precision of JWST, the star is making it really hard to do because of the stellar activity component. And that's where the giant planets offer us an opportunity to use those transits to model the transmission spectra and try and test those models. And the way we can test those models is see if we can detect a planetary atmosphere. And in this case, we do detect a planetary atmosphere at about 12 sigma. And I'll digress from going from the start to back to the planet, the original goal of our program. We detect a really weird planetary atmosphere. And it's weird because we detect no water. We detect no oxygen-bearing species, just a little bit of methane, which is shown in yellow, and maybe a little bit of hydrogen sulfide. So it's a very, very reducing atmosphere. Its metallicity is very low. And that's hard to explain currently. There's lots of caveats with this, obviously, especially with the transit light source effect, which I'm happy to go into later. But that's weird. The next part that makes even more weirder is the fact that the atmospheric metallicity is very discrepant from the bulk metallicity. So I mentioned those planet synth models that our collaborators are developing, and we use those and we predict the bulk metallicity, basically what fraction of the total mass of the planet is in its bulk elements. That's what's shown in the purple histogram. It's about 10 to 20%. I can go into the sources of uncertainty there, et cetera, et cetera. But the most important thing is that yellow region, which shows the atmospheric metallicity, is really far away from that purple region. So how do you form a planet that's fairly metal rich in its bulk, but its atmosphere is basically almost completely devoid of any metals in the astronomer's sense of the word metals? But again, we can come back to the solar system here. What we are seeing for Jupiter is the flipped case, where we're seeing that the atmosphere of Jupiter is enriched in metals, and we think Jupiter's interiors are devoid of metals. And the way we are explaining that now, and by we, I mean the planetary science community, is by invoking this deep radiative zone in Jupiter's interiors, based on the opacity, based on the abundance of alkali elements, and so on and so forth. One of the latest hypotheses to explain Jupiter's interiors, which we still don't fully understand, is the fact that there's this radiative zone at the kilobar level that decouples its outsides from its inside and can preserve this huge contrast between the bulk and the atmosphere. In the case of 5205, the first question is, do we expect such an interior structure? based on the formation entropy, based on the initial conditions of formation, et cetera, et cetera. So that's some of the work we are doing at the moment to try and see if we take similar interior conditions to Jupiter, put them on a planet like 5205, do we expect a radiative zone, which could explain this contrast between the atmosphere and the bulk? And that's kind of the basic goal of the GEMS collaboration. What we're trying to do is do a large survey of exoplanets, have enough that we can do statistics, and we're not worried about outliers, we're not worried about stochasticity, and then try and combine that with interior models of the solar system and try and combine the best of the both worlds, statistics of the exoplanets and the interior models of the giant planets. And we're not stopping over here. In the future, I think, Ravi, you mentioned metallicities. That's one of the big projects that we have that we're hoping to make progress on, which is study the metallicity dependence of these giant planets across the stellar mass, because that's one of the biggest votes for core accretion, that the fact that giant planets typically favor more metal-rich stars. And there's additional dimensions to this, which I won't go into for the interest of time, but this is really interesting to do, or really hard to do for M dwarfs, because as the plot on the right shows, as you go from higher mass to lower mass stars, the spectra just gets extremely complicated, because these molecules, which will otherwise thermally dissociate, like titanium oxide or vanadium oxide, or the hydrides even later, start to show up and basically erase any semblance of a continuum, which makes it really hard to get metallicity. So we're working with some undergraduate students on some stellar spectral synthesis. Again, I won't go into this right now, but if anyone is interested, I'm happy to discuss that. But we're having some success there, and I'm hoping we can at least start to have some reliable metallicity estimates for these M dwarf stars in the next few years, and hopefully expand that to elemental abundances after that, to try and actually perform the same kinds of tests on M dwarf stars, compare the atmosphere of the star to the atmosphere of the planet. But then the last bit I'll talk about that I think will be interesting to many folks in this room is our future plans. So we are starting off with the transiting survey because that's the best we can do at the moment. But the transiting survey is not, as you can immediately gauge from this plot, does not cover planets that are similar to Jupiter and Saturn. But it's the best we can do at the moment. It's the best we can do to understand where we are lacking in our models, where we are lacking in our understanding of planet formation, planet interior, statistical models, so on and so forth. But the goal is to do these transiting planets at the moment, measure their occurrence rates, so that in the future we can combine them with different detection techniques. So that in the future we can combine them with a radial velocity only sample that typically finds planets that are much further out. So those are the triangles I have shown over here, which are existing detections, and those start to go further out in semi-major axis space. But what I'm really excited about is the Gaia detections that are expected. So these are astrometric detections from ESA's Gaia mission, from the data release 4 that's supposed to come out in the next year or two. And that's for the first time going to provide us statistics at solar system-like separations for planets. And it's only around M dwarfs will Gaia have the sensitivity to look at giant planets in the solar system-like regime. And that's the key bit. If we can test our models at the moment with those transiting planets, figure out how we can do the best job of improving them and preparing for Gaia DR4 in the next 2 to 3 years, that's when we can really start to look at solar system-like separations in a statistically rigorous sense. And then the last bit to this, which I'm excited about, and I think lots of folks in this room are excited about, is Roman. So with Roman, we can do microlensing, and now microlensing is looking at much further out planets. And I'm focusing on the microlensing here, not the transiting survey. But now the microlensing planets are going to be not just further out, but they're going to be interesting because they're looking at a completely different part of the galaxy. Completely different part of the galaxy in terms of the alpha element enhancement, in terms of the star formation history, in terms of the ages of the star and their metallicities, et cetera. Axes we haven't been able to probe in a rigorous manner so far. So that's kind of the goal for the GEMS collaboration, to try and start really close to the host star, which is the best we can do at the moment for these transiting planets, and then move further out with these future missions, starting from Gaia to Roman, and start to map out this region of parameter space, which is the semi-major axis. And then hopefully we have the USCLT program, which will help us perform detailed characterization on a select subset of this. So I'll leave in my outline, which is basically how I discuss how we are trying to contextualize the solar system with the GEMS survey, both from the ground and from the space. I didn't discuss a few aspects because I already had too many slides. So I'm hoping if people are interested, we can talk about some of this. Some of these are ideas about spectral synthesis. Some of these are astroseismology with JWST, trying to map the surface of the star, et cetera, et cetera. But maybe I should have. I mean, we're all astronomers. Everything looks fine in log space. But I'm hoping we have some time at the end for questions. So I'll leave my conclusions up and have to take more questions.
Awesome, thank you so much. So does anyone have any questions in the room or online? I guess feel free to ask questions in the chat online or raise your hand and we can call on you. Or maybe we'll start with Simone.
Thank you. So thank you for your talk. It was very
Absolutely.
interesting. You mentioned that disk instability has a potential formation pathways for your planets, but this formation mostly occurs at the outer part of the
Yes.
system. So probably that this planet observed by transit just migrates through
Yes.
the system. So my question is, do you also consider measure of orbits parameters such as eccentricity or inclination that could help to constrain the formation pathway?
Yeah, so for all of these planets, as far as we can tell, to the best of our measurement precision, they're circular orbits. The problem you mentioned of migration is true regardless of core accretion or GI for these objects, because these objects are so massive compared to the host star, they cannot form in situ. So even for core accretion, they have to form maybe at 5 or 10 AU, maybe 2 to 5 AU, and then migrate inwards. It's definitely worse for gravitational instability, is probably 5 to 10 AU. In fact, if I go back to those slides, that's typically where we consider that they form around the 5, if I can make this work, around the 5 AU separation. So definitely, we have to invoke some formation, some migration mechanisms. Either that's through high eccentricity migration, which then dampened out, or through disk migration. But also the thing we have in gravitational instability is those density perturbations in the disk. And those spiral waves can be very helpful to make the planet migrate inwards. But they should also impart a high eccentricity at the end of the day. So the question, irrespective of the migration, is if it's through an eccentricity-driven migration, you have to dampen it out. And do we see that in their present-day properties or not? We do not exactly know yet.
Okay, thank you.
I'll ask one.
Yes.
So maybe you sort of touched on this, but going way back to kind of a similar topic of the kind of dearth of the very massive M-dwarf disks to explain these more massive M-dwarf planets. I mean, could that just be like sort of a survivorship bias that when you have a disk that's massive enough to form these planets, they just collapse and all of the materials gobbled up, forming these more massive planets?
That's a really good question. So maybe. So the problem comes down to the fact that if we think about the average occurrence of these planets, it's on the order of 0.1%.
Sure.
So to observe a disk that's comparable with the 0.1% occurrence rate, you need to have a sample of at least 1,000 disks.
Sure.
And even if we take all the ALMA disks, we don't have a sample of 1,000 disks, let alone separating it along the stellar mass axis. So the odds are that we haven't observed one of these M-dwarf really massive disks that are forming giant planets. But now the other piece to that, the caveat to that is we have the bias of magnitude. So in principle, it should always be easier to find and detect and characterize more massive disks.
Right.
So it's possible that we have observed that one of those ALMA disks that I was showing, once we account for those biases, are indeed massive enough to explain a giant planet, but it's just hard to tell with the current sample.
Right.
So without the occurrence of the disks, or what's the occurrence of a certain disk mass around a certain stellar mass, it's really hard to answer the question you posed, which is, can you compare the occurrence of those disks with the occurrence of those planets? And is there a difference between the two? Because that would directly point to what you just said. Okay. Are there any questions on this? Okay.
Just us.
Oh, yes.
So kind of a two-parter. So firstly, so TESS has found more gems than RV only surveys.
Yes.
Is that right? And so I guess my question is, why is that? Just because RV surveys are not biased towards these faint M-dwarfs, or they're biased against observing faint M-dwarfs, even though the signals are large around giant planets?
Numbers of targets.
That's a wonderful question. So I think the first part to that is the test is finding so many of these because it has observed 1 million M dwarfs on the order of.
Yeah.
But the fact that we are finding any in radial velocities when they have looked at, let's say 100, 200, but let's say on the order of 100 planets, 100 stars, and they have found, I don't know, let's say 10 giant planets, is that there are many, many more transiting, non-transiting, much further out giant planets around M dwarf stars. And this is not surprising because we know this for solar type stars, that the occurrence of giant planets goes up as you go further out. And I think what's going on is something similar, where the reason TESS is detecting them, even though it's at such the low bottom end of the occurrence rate, is because it has just this huge input function, or huge input sample. And that's what we're trying to make the most of, to do these statistics. But the fact that RVs have found even one, let alone, I don't know, 10 of them, means that there are many, many more of them to be found through Gaia. Was there a second?
Well, I guess on that same vein, I know you didn't talk about like the Roman transiting survey.
Yes.
But I guess
Yeah.
it's a similarly.
Yes,
You're gonna expect some population.
Yes, so if I were to make a similar shaded region for Roman, because Roman has a much longer staring window, it would go further out. But now the questions to that are, Roman's sample of M dwarfs is going to be smaller, but it's going to be much more metal rich. So now if giant planets around M dwarfs also are enhanced as a function of metallicity, can you compensate for those two effects? I do not know. But that would be a very good way to test exactly that. But with Roman, that would probably be in a probabilistic Bayesian sense, because I don't know if it'll be easy to pinpoint which star is the transit host or so on. So maybe we can have a catalog of Roman transiting planets based on assumptions and test that again once we have their occurrence. But yes, absolutely, it will help push us beyond TESS in terms of the semi-major axis. Oh,
Yes, I have a
Jamila?
question.
Yes.
It's sort of half-baked, so I'm gonna try to
Easy.
explain my question. So when we're talking about, I know you talked about connecting to the planet synthesis models and the things that we're observing in these planets in our solar system. Is the plan to do that from the bulk property standpoint or from the more atmospheric characterization standpoint? And if like a lot of this complexity that we're seeing in the solar system, like planets is like inwards of like
Yeah.
a certain boundary, how would we be able to do that with atmospheric characterization?
Yeah, no, that's a very real problem. And because the atmosphere is like this tiny onion skin on the top, and most planetary scientists don't care about the atmosphere because they're focusing on what's 99.999% of the planet's mass. And what we are probing with GWST is such a tiny sliver on the top that, yeah, how much does it represent the bulk? And if we are to believe 5205, it does not represent the bulk at all. And that's why we need to invoke these different mechanisms to try and decouple the two. This is a real problem. How do you take what's measured at the millibar level and try and associate that with what's at the kilobar level? Maybe you can do slightly deeper with emission. Maybe you can go from a millibar to maybe 100 millibar. But that's still a very, very tiny part of the planet's atmosphere. So what you need to do is then start invoking GCM models, which you use to invoke to couple your atmospheres with the deep interiors. But as you can imagine, anytime you do that, there's so much wiggle room and extrapolations that your uncertainties balloon. So just hard, essentially. Yeah.
Has anyone plotted, we now have a lot of these atmospheric metallicities for not just M stars,
Yes.
planets around for the transmission spectroscopy. And of course, you can do this. Has anyone plotted this model bulk heavy element mass fraction for all the?
Not yet. No.
See it?
No.
Maybe there's no correlation, which means that we have a huge problem in trying to assume that the bulk mass fraction calculation is even correlated at all.
So yes, so the one problem with that is, so firstly, this is easier to do for giant planets because you have fewer elements to consider, so your degeneracies are better. But the second problem is most of the giant planets that have been looked at so far are hot Jupiters. And those interior models don't apply to hot Jupiters because we still don't have a good handle for what inflates hot Jupiters. So all of these models only work in the warm Jupiter territory. Luckily for GEMS, all of those are in the warm Jupiter territory because they are so cold. So we'll definitely be doing that for the GEM sample as a starting point. But I think just by virtue of the community putting in a lot of other proposals for warm Jupiters, the sample of warm Jupiters is growing. And I would expect that towards the end of cycle 3, we could do that outside of GEMS as well for an FGK warm Jupiter sample and compare that with the GEM sample. But hopefully soon, not yet. Any other questions?
Awesome. Well, if there's no other questions, let's thank Shubham again. Next talk announcements.
There's a lot.
Yeah. Stay tuned.
Look at your email.
Yeah.
But thanks everyone for coming online. I'm gonna end the meeting now. And for everyone